Nuclear Magnetic Resonance Spectroscopy, Chapter 15. Objectives: 1. Nuclear magnetic resonance or NMR spectroscopy. 2. 1H NMR. 3. Carbon-13 NMR. And 4. DEPT or DEPT. Your goals. By the end of the chapter, you should be able to understand and interpret 1H NMR and carbon-13 NMR spectra, predict chemical shifts, predict splitting patterns. Let's begin. 1. Nuclear magnetic resonance or NMR spectroscopy. It may be the most powerful method of gaining structural information about organic compounds. NMR involves the interaction between electromagnetic radiation, EMR or light, and the nucleus of an atom. We're going to focus on carbon and hydrogen nuclei for analysis of organic compounds. The structure or the connectivity of a given molecule affects how the radiation interacts with each nucleus in the molecule. Nuclear spin. Protons and neutrons in a nucleus behave as if they are spinning. If an atom has an odd number of protons and/or an odd number of neutrons, it will have a net nuclear spin. Some example isotopes that have net nuclear spin include 1H, carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. The spinning charge in a nucleus creates a magnetic moment. A magnetic moment of a proton means we have a magnetic field that is generated, just like a bark magnet's magnetic field, as we can see here in figures A and B. The magnetic moment exists perpendicular to the axis of nuclear spin. Alignment, spin states, and spin flips. If the normally disordered magnetic moments of atoms, like we see in figure A, no magnetic field, they're disordered. If they are exposed to an external magnetic field or B naught, like we see in figure B with the blue arrows, their magnetic moments will align with the field or against the field. If they're with the field, we give them the symbol alpha. If they're against the field, we give them the symbol beta. The beta spin state is opposing the external magnetic field, and it has a higher energy spin state. The alpha spin state is aligned with the external magnetic field and has a lower energy spin state. At this point, when the atom is then in the alpha state exposed to radio waves with just the right amount of energy, or delta E, the photons are absorbed and spin flips are observed to the beta spin state. So note, from alpha to beta, that requires energy, and that energy is in the radio wave frequency. The stronger the magnetic field that these atoms are exposed to, then the greater the energy gap will be, or the greater the delta E. Deshielded nuclei. The external magnetic field will also affect electrons. It causes electrons to circulate, inducing an opposing magnetic field or diamagnetism. The nuclei therefore experience a lower external magnetic field and are said to be shielded, requiring less energy to spin flip. Nuclei surrounded by less electron density are said to be deshielded. Radio wave and molecular structure. The amount of radio wave energy necessary for the alpha to beta energy transition depends on the electronic environment for the atom. When the alpha spins are flipped to beta spins, energy is absorbed, and the atoms are said to be in resonance. The use of the term here, resonance, is totally different from when we're talking about electrons and molecular orbitals. The amount of energy required for each 1H to flip tells us about its electronic environment and thus the molecular structure of the compound. Magnetic field requirements. NMR requires an external, strong magnetic field and radio wave energy. The strength of the magnetic field affects the energy gap. The strong magnetic field is created when a high current is passed through a superconducting material at extremely low temperatures at about 4 Kelvin. The greater the current, the greater the magnetic field. Instrument and FID or FID. Pulse Fourier transform spectrometer uses a brief pulse of radio energy at all the relevant wavelengths to excite the sample. Each of the atoms is excited and then relaxes, emitting energy. The emitted energy is recorded as a free induction decay or a FID. The FID contains all the information for each atom. A mathematical treatment called a Fourier transform separates the signals so an individual signal can be observed for each atom that was excited. Often, multiple FIDs are taken and averaged together. NMR sample. Before analysis, NMR samples must be prepared neat or in a liquid solution. If a solvent is used to make a liquid solution, the solvent must be deuterated. It has to have either 2H or deuterium present, but no 1H present. A common solvent is chloroform D1 or CCl3D. The sample is placed in an NMR tube and inserted into the instrument. The tube is spun at a high rate to average magnetic field variations or tube imperfections while the sample is exposed to a high magnetic field. The sample is generally at room temperature when collecting the 1H NMR spectrum. 2. 1H NMR. NMR spectra contain a lot of structural information. We will consider the number of signals, signal location or the chemical shift, signal intensity or the area under the signal, signal shape or the splitting pattern. We will analyze all of these characteristics of a 1H NMR spectrum, which looks like the spectrum you see here below. Number of signals and homotopic protons. The number of signals in a 1H NMR spectrum indicates the number of different kinds of protons in a compound. Identical protons are chemically equivalent and will give the same signal. The way that we can tell that we have chemically equivalent protons is if they fall into the category of either being homotopic or enantiotopic. Homotopic protons. If the molecule has an axis of rotational symmetry that allows one proton to be rotated onto the other one without changing the molecule, it's chemically equivalent. Another test for homotopic protons is to replace a proton one at a time with another atom. If the resulting compounds are identical, then the protons that you have replaced are homotopic. Number of signals and enantiotopic protons. These protons occur if the molecule has a plane of reflection that makes one proton the mirror image of the other. The replacement test is universal. It will work to identify any equivalent protons, whether they are homotopic or enantiotopic. If the resulting compounds are enantiomers, then the protons that you replaced are enantiotopic and are chemically equivalent. They will give one signal. Diastereomers. If the replacement test produces diastereomers, that means that the protons are not chemically equivalent, and each proton will produce its own signal. The number of signals. To determine if protons are equivalent and therefore giving one signal, look for rotational symmetry or an axis of symmetry. If there is one, they're homotopic. But if there isn't any, then look for a plane of symmetry, and if there is a plane, they are enantiotopic. If they're enantiotopic or homotopic, they will be chemically equivalent. Otherwise, they are not chemically equivalent and will give rise to their own signals. Let's take a look at this example here. If we consider 2-butanol and just consider the 2 hydrogens that are on carbon number 3, these two here are not chemically equivalent. Because they're not chemically equivalent, they're not interchangeable by rotation symmetry or reflectional symmetry, they're going to give rise to their own signal. The number of signals and shortcuts. There are some shortcuts that you can take to identify how many signals you should see in the 1H NMR spectrum for a given compound. 1. The 2 protons on a CH2 group will be equivalent if there are no chiral centers in the molecule. 2. The 2 protons on a CH2 group will not be equivalent if there is a chiral center in the molecule. Here are a couple examples. The first molecule has a CH2 group the two protons are equivalent because there are no chiral centers in the molecule. However, in the second example, there is one chiral center, so the two protons are not equivalent and will give rise to their own signal. 3. The three protons on any methyl group will always be equivalent to each other. And 4. Multiple protons are equivalent if they can be interchanged through either rotation or a mirror plane. Take a look at this very symmetric ketone. Because there is an internal mirror plane, that means that we can have interchange between protons of different carbons. Therefore, we have high symmetry and chemically equivalent protons. The very end carbon, carbon 1 and carbon 5, these are methyl carbons. Each one has 3 H's, and the 3 protons are chemically equivalent to each other. As well, carbon 1 and carbon 5 protons are equivalent. Therefore, the 6 H's will have one signal. Then we also have on carbon 2 and on carbon 4, we have CH2s there, and all of these protons here are chemically equivalent to each other. So we would expect to see one signal for the CH3s and one signal for the CH2s. Let's consider an example compound cyclohexane. Recall that cyclohexane chair conformations have 6 equatorial and 6 axial protons. The axial and equatorial protons have different electronic environments. Technically, there are 2 types of protons here, so one would expect 2 signals. However, only one signal is observed in the 1H NMR. That's because at room temperature, the chair interconversion occurs rapidly. That is, the axial positions become equatorial and vice versa pretty quickly. So the NMR is not fast enough to see the individual structures, so the average is observed or only one signal. However, if the temperature is reduced to -100 degrees Celsius, ring flipping is slow enough to observe the 2 signals. The standard and the chemical shift. In many NMR solvents, 1% TMS or trimethylsilane is added as an internal standard. The frequency of the protons in TMS is lower than that observed for most organic compounds. The shift for a proton signal is calculated as a comparison to TMS. Units given the symbol delta are often in parts per million or ppm, which simply indicates that signals are reported as a fraction of the operating frequency of the spectrometer. So we have the shift from TMS in hertz observed for the substance over the operating frequency. For benzene, if we consider its shift on a 300 megahertz instrument, it is at 2181 hertz, and then if we consider the delta, that's at 7.27 times 10 to the negative 6, or 7.27 parts per million. On a 60 megahertz instrument, the signal for the benzene protons is at 436 hertz. But if we then divide that number by the operating frequency of the spectrometer, it's also at 7.27 times 10 to the negative 6, or 7.27 parts per million. The hertz of the signal is different in different instruments, but the shift is still relative to TMS, and it's constant. Most signals that we're going to see for proton NMR will be between 0 to 10 parts per million. Chemical shift, downfield and upfield. Early NMR analyzed samples at a constant energy over a range of magnetic field strengths. Due to that, if we had to use a low field strength, we would call that downfield, and at high field strength, we would call that upfield. Shielded protons require a stronger external magnetic field to be excited at the same energy as de-shielded protons. So upfield means the protons are shielded, downfield means the protons are de-shielded. Chemical shift, high and low energy. Current NMRs analyze samples at a constant field strength over a range of energies. Shielded protons have a smaller magnetic force acting on them, so they have smaller energy gaps and absorb lower energy radio waves. They are still said to be upfield. Higher energy requirements are needed for de-shielded protons, and we see that these are downfield. Chemical shift, alkanes and alkyl halides. Alkane protons generally give a signal at around 1 to 2 parts per million. To predict chemical shifts, let's start with the standard ppm for the type of proton. Methyl protons give a signal at about 0.9 ppm, methylene protons at about 1.2 ppm, and the methine proton at about 1.7 ppm. In alkyl halides, protons can be shifted downfield when nearby electronegative atoms cause deshielding. So consider these monohalogenated compounds. The default or the standard methane has a shift at about 1.0 ppm for its protons, but the proton's signals continues to go downfield as we increase the electronegative atom attached to alpha carbon, with fluoromethane having its protons found at 4.3 ppm. The effect on beta protons is about 1/5 the effect on alpha protons. Alpha protons will sense the most deshielding, therefore those are going to be downfield significantly, but beta protons will not be as downfield, but will be more downfield than before, and gamma protons will be found approximately where we expect them to be found. Increase in electronegative atoms can also cause more deshielding and downfield shifting. For example, consider the monohalogenated chloromethane. The hydrogens are going to be found at 3.1 ppm. However, if we increase the number of electronegative atoms, in this case Cl, the shift also goes more downfield, 5.3 ppm and 7.3 ppm for the monohydrogen compound chloroform. Shift predictions table. The table helps us determine the effect of neighboring functional groups on the chemical shift. This is a very limited table, so one may use handbooks or tables found online at credible websites to determine functional groups beyond this table. But let's consider alpha protons. Alpha protons that are part of either an alcohol or an ether functional group should be about 2.5 ppm more downfield than their original location is as expected. For example, methylene groups should be at 1.2 ppm, but because they're on alpha carbon, they're going to be at 3.7 ppm or about 2.5 ppm more downfield. If the alpha protons are part of a functional group containing an ester, then we expect them to be about 3 ppm more downfield. So methylene group again expected at about 1.2 ppm. Because they're alpha to an ester, 3.0 ppm would be what we have to add, and we would expect it at around 4.2 ppm. If they are on an alpha carbon of a carbonyl group, then we would then expect them to be about 1 ppm more downfield, or about 2.2 ppm. Please note that these are approximations. Chemical shift and the anisotropic effect. When the electrons in a pi system, such as benzene, are subjected to an external magnetic field, they circulate and produce their own magnetic field, causing diamagnetic anisotropy. That means that there's going to be different regions of localized space experiencing different magnetic field strengths. Regions outside the ring will feel or sense an increased magnetic field. The result of diamagnetic anisotropy effect is really about the effect that it has on aromatic protons and deshielding them. More magnetic field means more energy is required to do the spin flip of those protons. Aromatic protons will then appear at about 7 parts per million. Consider this H-1 NMR of this aromatic compound. Notice how the aromatic protons are significantly downfield, so we can attribute these to these H's here that are attached to this benzene ring with this functional group, in this case an alkyl group, on the ring. These are actually upfield. We have here a signal for some of those protons and a signal here for the other set of those protons. More on aromatic protons. The result of the diamagnetic anisotropy effect is like shielding for protons on the inside of the pi system. Protons outside the ring are going to appear at about 8 ppm for 14 annuli, but those inside the ring are about -1 ppm. Common chemical shifts. It is necessary to be familiar with the ppm values of these common types of protons. Earlier we talked about methyl, methylene, and methine protons, but you should also be familiar with allylic, alkenyl, aromatic, alkyl halide, alcohol, vinylic, aryl, aldehyde, and carboxylic acids. Integration. The integration, or the area under the peak, quantifies the relative number of protons giving rise to a signal. A computer will calculate the area of each peak, representing that area with the step curve. For example, here is a proton NMR of a given compound, and we can see the step curves here, or the integration. The computer operator sets one of the peaks to a whole number to let it represent a number of protons. For example, it represents this area as 1, and everything else is in reference to 1. The computer uses integration ratios to set the values for the other peaks. Integration represents the number of protons, so then you must adjust those values to whole numbers. If the integration of the first peak is doubled, the computer will adjust the others according to that ratio. So if it's supposed to be 2 protons for this signal, then the rest are going to be multiplied by 2 in order to give the actual ratio. Integration is relative, not absolute. The integrations are relative quantities rather than absolute count of the number of protons. And symmetry can also affect integrations. For example, 3-pentanone has only 2 kinds of protons, the methyl and the methylene. The relative integration values of the 2 signals will be 2 to 3. But because we have a molecular formula of C5H10, that means it can't be 2 to 3, but rather 4 to 6. Multiplicity and n+1. Multiplicity, or the splitting pattern, is the number of peaks in a given signal. Multiplicity results from magnetic effects that protons have on each other. The table shows how the multiplicity trend continues. Consider the number of neighbors a given proton has. That number will then dictate the multiplicity, or the splitting pattern, for the signal. The intensity of individual peaks follows Pascal's triangle. By analyzing the splitting pattern of a signal in a 1H NMR spectrum, you can determine the number of equivalent protons on adjacent carbons. The trend in the table also allows us to predict splitting patterns. When there are n number of neighboring protons that are chemically equivalent to the proton that we are looking at signal, there will be n+1 in the signal in terms of peaks. If there are no neighboring protons, we would then expect the multiplicity to be a singlet. If there is one neighboring proton, n+1 tells us 1 + 1, it should be 2, or it will be split into a doublet. A triplet would be split because of 2 neighboring protons that are chemically equivalent. 2 + 1 gives us 3. A quartet would be due to 3 equivalent protons that are neighboring the proton that's giving this signal here. And we can continue on. Notice the intensity of each of the peaks follows Pascal's triangle once again. Doublet. Let's consider protons HA and HB. HA will have a signal that will be split due to HB. Since HB is only one neighboring proton, n+1 tells us that A signal is going to be split into a doublet. Why? There are going to be 2 ways that the proton can align with the external magnetic field. HB, or the neighboring proton, can align either against the field or with the field. That causes HA to have 2 different magnetic environments. So HA will appear as a doublet. Now let's consider HA having 2 neighboring protons. The 2 neighboring protons HB will have different ways that they can align with or against the magnetic field. Both HB protons can align against or with, or one with and one against. because there's two neighboring protons, HA signal will be split into a triplet because n plus 1 or 2 plus 1 is 3. Quartet. Now let's consider HA signal when it is adjacent to 3 chemically equivalent protons, HBs. Because there's 3 of them, n plus 1 tells us 3 plus 1 should be a quartet. So HA signal will be split into a quartet. In terms of intensity, notice the different possibilities of how the protons HB can align with or against the magnetic field. All 3 can be against the field or with the field, or 2 can be aligned against and 1 with, or 2 with and 1 against, but in different patterns. Splitting rules. Remember 3 key rules for splitting. 1. Equivalent protons cannot split one another because they resonate together. 2. To split each other, protons must be within a 2 or 3 bond distance. We will see splitting whenever we have protons that are not equivalent, either geminal or vicinal. However, if they're too far apart, we're not going to observe splitting. 3. The n plus 1 rule only applies to protons that are all equivalent. The splitting pattern observed for the proton shown below will be more complex than a simple triplet. So this proton here, even though we know that there is a hydrogen here and a hydrogen here, there's 2 of them, because those 2 protons are not chemically equivalent, we're going to have complex splitting. It will not be n plus 1 or a triplet. Complex splitting will be discussed later in this section. The coupling constant. The degree to which a neighbor proton will couple to its neighbor is called the coupling constant, or the J value. Before we begin considering the J value, let's look at this molecule here. The molecule here has 2 different types of protons. HA are equivalent protons and would give 1 signal. HB are also chemically equivalent to each other and would give rise to 1 signal. We would expect 2 signals. HA has a neighbor, HB, of 3, so HA signal will be split into n plus 1, or 3 plus 1 equals 4. We expect a quartet for the signal of HA. For HB, the HB protons have as neighbor HA, there's 2 of them, n plus 1 or 2 plus 1 gives us 3. We expect the signal for HB to be split into a triplet. Now we're going to talk about the distance between peaks that are adjacent to each other in a given splitting pattern. The J value is a distance measured between peaks of a splitting pattern, and it's measured in Hertz. Protons splitting each other will have the same coupling constant. In other words, the splitting pattern that we see here will have a distance between peaks in Hertz, JAB, that will equal the splitting pattern here for the signal HB, also in Hertz. Higher field strength. Higher field strength instruments will give rise to better resolution between peaks, because the coupling constant is a much smaller percentage of the overall Hertz available. Consider this ester and the signals that are given by protons B and protons C. If one uses a 300 MHz spectrometer, the peaks that are noted are not going to overlap. We avoid overlapping altogether, and we can see distinct signals for protons B and protons C. If, though, one uses a 60 MHz spectrometer, note that there is overlap between the signals given by protons B and protons C. It's a lot easier to tell and distinguish between protons B and C using a higher megahertz spectrometer. Patterns. Sometimes recognizable splitting patterns will stand out in a spectrum. Make sure that you pay attention to these patterns because you might see them quite a bit. An isolated ethyl group gives rise to a triplet and a quartet. Whenever we have ethyl, CH2CH3, in the NMR spectrum, we expect a triplet and a quartet. The triplet and quartet must have the same coupling constant if they are splitting each other. Notice how the distance between peaks here of this quartet does not match the distance between the peaks here in this triplet. Therefore, this cannot be an ethyl group. A peak with an integration equal to 9 suggests the presence of a tert-butyl group. So if we have a singlet with the integration of 9, that usually means we have a tert-butyl group. An isolated isopropyl group gives rise to a doublet and a septet. So here is an isolated isopropyl group. We have the CH3s that are in resonance with each other because they have one different proton that is adjacent. That's going to be n+1 or 2. So we'll see a doublet here for those 6 hydrogens. And this hydrogen has 6 protons that are not equivalent to itself but are chemically equivalent to each other. So 7 would be the number of peaks we expect because n+1 or 6 + 1 gives us 7. Complex splitting. Complex splitting results when a proton has 2 different kinds of neighboring protons. In the molecule shown, HB is split into a quartet by HA and into a triplet by HC. So here's HB. HA, there's 3, so 3 + 1 is 4, quartet, and there's 2 HCs, so 2 + 1 gives us a triplet. Now, because they're not equivalent, we're going to see complex splitting. If the coupling constant between A and B is much greater than B and C, then the signal will appear as a quartet of triplets. If the coupling constant between BC is much greater than the coupling constant between AB, the signal will appear as a triplet of quartets. If BC and AB coupling constant are pretty similar, then several lines may overlap and we'll get a signal that we refer to as a multiplet. Splitting not observed and signal broadening. Splitting is not observed for some protons. Consider ethanol. The protons bonded to a carbon will split each other, but the hydroxyl proton will not split. Note here that the CH3-CH2 protons are splitting each other. The CH3 signal is being split into a triplet because the CH2 is 2 protons plus 1 gives us 3. So this triplet here is due to the 3 protons of methyl. The CH2 is being split into a quartet because it is sensing 3 protons plus 1 gives us 4. So this signal here is due to 2 protons, or the CH2. But this singlet here is due to the hydroxyl H. It is not split. As well, the hydroxyl proton and other exchangeable protons can undergo rapid exchange with trace amounts of acid. In other words, they can be swapped around. That exchange will blur the shielding-deshielding effect of neighboring protons, giving a singlet that is oftentimes broadened. Distinguishing compounds using 1H NMR. These 3 molecules below might be difficult to distinguish by just using infrared spectroscopy or IR and mass spec. But we can easily distinguish them by using 1H NMR because they do not have the same number of equivalent protons. For example, the first molecule will give rise to 3 signals in the 1H NMR. The second one will have 4 signals, and the last one would have 2 signals. Analyzing a 1H NMR spectrum. With a given formula in 1H NMR spectrum, you can determine a molecule structure by a 5-step process. 1. Calculate the degree of unsaturation or hydrogen deficiency, index HDI. 2. Consider the number of NMR signals in integration, which gives us clues about the symmetry in the molecule. 3. Analyze each signal and draw fragments consistent with each signal. 4. Assemble the fragments into a complete structure. And then 5. Verify the proposed structure is consistent with all spectral data. That means IR, mass spec, etc. 3. Carbon-13 NMR. Because 1H is by far more abundant isotope of hydrogen, 1H NMR signals are oftentimes very strong. But carbon-13 accounts for about 1% of carbon atoms in nature, so a sensitive receiver coil and/or concentrated NMR sample is needed. In 1H NMR, shift, splitting, and integration are really important. But in carbon-13, only the number of signals and the chemical shift will be considered. Overview of carbon-13 NMR. In carbon-13 NMR, the proton carbon-13 splitting is often so complex that spectrum is unreadable. To elucidate the carbon-13 spectrum and make it easier to determine the total number of carbon-13 signals, carbon-13 NMR are generally decoupled. In the vast majority of carbon-13 spectra, all the signals are singlets. Compared to 1H, carbon-13 atoms require a different frequency of energy to excite or to resonate. Compared to the standard TMS, carbon-13 signals tend to appear between 0 and 220 parts per million. Each signal in a carbon-13 NMR spectrum represents a unique type of carbon. Planes and axes of symmetry can cause carbon atoms to be electronically equivalent. Symmetry and the number of signals, shift, and shielding. Note how symmetry affects the number of carbon-13 signals for these compounds. Now we're looking at carbon. So here in the first one, we have a plane of symmetry here. So we expect 4 signals, with this one here, 5 signals, and with this one here, 3 signals. Like 1H signals, chemical shifts for carbon-13 signals are affected by shielding or deshielding. For example, if we have sp3 and sp carbons that are due to alkane, maybe CN, CO, C triple bond C, CX, we're going to see them below 100 ppm. But the more deshielding, the higher in ppm we're going to find these carbon signals. Up here we'll see C double bond O, C double bond C, aromatic signals above 100. Patterns in carbon-13 shifts. Here are some general shifting patterns. Note the chemical shift will increase if we have more deshielding present. Methyl carbons, methylene carbons connected to 3 or 4 R groups, notice that they're under 100 ppm, under 60 ppm even. Connected to iodine, connected to bromine, still under 100 ppm. Here connected to nitrogen, connected to chlorine, and singly bonded connected to oxygen, still under 100. We're getting close to 100 if we have C triple bond C carbons. C double bond C carbons are above 100, aromatic 110 to 170, and carbonyl carbons, we can see them as high as 220. 4. Depth or DEPT. Carbon-13 spectra generally give singlets that do not provide information about the number of hydrogen atoms attached to each carbon. Distortion as enhancement by polarization transfer or depth, carbon-13 NMR provides information about the number of hydrogen atoms attached to each carbon. There's 2 different forms to see depth, either the 90 or the 135. Only CH signals appear, so we would only see CH signals in depth 90. But what's oftentimes more useful is depth 135, because we will see as positive signals carbons with an odd number of hydrogens like CH3 and CH, and we'll see upside down peaks for an even number of hydrogens, CH2. C with no hydrogens will not give rise to a signal. MRI as an example that we can take note of in the medical field. MRI stands for magnetic resonant imaging, and these instruments are basically 1H NMR spectrophotometers. The body is analyzed rather than the sample in an NMR tube. Different tissues have different concentrations of protons. The MRI then gives a 3D image of different tissues. Radio waves and magnetic fields are very mild, so no side effects are experienced.